morning. It's a pleasure to be here. So I'd like to first acknowledge and thank Rainer and Monica for organizing this. So this is an amazing event. And I'm really happy to be here. So it's a little bit tough to talk right now, right? Because I think I drank too much cider yesterday. But but I hope you're going to get sick with my voice because it's a 1.5 hour talk. So if you have any questions, you can ask me anytime, right? So so I'm Raul Freitas from the Brazilian Synchrotron. And I'm here to talk about infrared spectroscopy at the nanoscale, right? But I think the reason that I'm here is that synchrotrons are pretty good broadband source in the infrared range, and that's the main driving force, I think. So just for you to have an idea, so I come from Brazil, right? So Brazil is a big country, and I took, of course, just a small slice here with a state that you know, a city that you know well, right? So São Paulo state is the place that I work, and São Paulo city is a city more or less 600 kilometers from Rio de Janeiro, and Campinas is the city that we have the institute. So Campinas is more or less 100 kilometers from São Paulo city, right? So in Campinas is a big city, so 1.5 million people live there. And we have the State University of Campinas, is one of the top universities in Brazil. And the lab is just beside the State University there. So that's the picture of the institute. So that's the Synchrotron lab, of course. But we have here three other national labs, one lab for nanotechnology, another national lab for biosciences, another one for biorenewables. They usually try to develop second-generation fuels like sugarcane alcohol from the biomass, but now they expanded their business. And of course, we have the Brazilian Synchrotron lab, which is the place I work. So there is an infrared beamline in here that I will talk a little bit about this. But the university is, here's the Campinas city, and the university is just beside here. So, all right. So I will not bother you much about, synchrotron stuffs, but the way we generate radiation is accelerating particles. So we take electrons, we accelerate at close to the speed light, and every time we actually make these curves in this storage ring, we have the radiation coming out. So we collect this radiation here, and we distribute to two stations that we call Imbuya. Imbuya is the name of a Brazilian tree, and that's the name of the beamline that I coordinate. And we have a nano station and a micro station. Micro station is just classical infrared microscopy within the diffraction limit, and the nano station is dedicated to nano-FTIR. So that's basically the station we have there. And the project is new, so I forgot to say here that we used to operate in a smaller ring here, and we shut down in 2019, and then we moved to this big guy here. We call this machine Sirius. That's the name of the machine. And it's, just for you to know, it's a good name. It's a 4th generation machine. So it means that it's the newest technology for synchrotrons. So there are only 2 more in the world operating right now, one in Lund in Sweden, and the other one in France in Grenoble, right? So basically, they do amazing stuff with X-rays, like coherent diffraction, nanoprobes with X-rays, and so on. But it's also, I will show you quickly, that it's a good machine for infrared as well. So this is a near-field spectrum that we took still in the commissioning time. We were testing, And I think it's very fainty here, but the wave numbers here is, this is 1,000 and this is 10,000. So we are talking about a very broadband spectrum covering almost the whole MCT sensitivity in just one experiment, right? So we had some improvements here. I'm not here to talk about this, but something that Kaiman presented that I found very interesting is that you have this, let's say, chromatic distribution at the tip, and somehow the instrument or the technique is magical that compensates the scale of these wavelengths that reach the tip and the propagation length to produce these enhanced fields. And the technique actually can handle this sort of monster spectrum that comes from mid-IR up to almost visible, right? So this is I think it's you can comment afterwards, but you can say that this is something very impressive from the technique, that you can handle such large number of energies in just with a classic tip. I mean, this is a PTIR tip. It's a commercial tip. So
those dips in the spec are from the source or the interferometer?
This is the environment. So this is just see.
No. Those they look like periodic. Right?
These ones?
Yeah.
This is water overtones.
It's only the water.
Just water vapor. So you have the first one here, but we have the second, the third, and the fourth here. So it's like just water. This is CO2. This is something related to the diamond window that we have. And the cut here is just because we have a calcium fluoride window. We didn't have another window by that time, and we are cutting part of the, let's say, low energy part of the spectrum. But it's just for you to have an idea of that synchrotrons, they have this kind of spectrum, and this is working in the near field experiment. All right, so if you want to know more about this facility, you can go to this website. It's an open facility, so as Luca was saying for the Felby, this is also a facility that you can submit your proposal and you can do your research there. So you can find more information here. And we have a set of equipment beside the synchrotron. We have also a DFG, mid-IR. We have a QCL to do imaging in the mid-IR as well, and some visible lasers for plasmonics and stuff. All right, so now let's come back to the subject, right? So I put here a few works that I find that they are quite decisive for the definition of nano-FTIR as a robust technique. And the first one is not exactly a Fourier transform experiment, but I think it's a broadband spectroscopy experiment that sort of inspire afterwards this. I think this is something that I know that's a dual comb experiment here, but I just want to highlight that there are other experiments before the nano-FTIR, but this is something that is already very, let's say, powerful, that you can reconstruct this broadband response of the materials. And then this was in 2006, led by Kaiman, and then 5 years ago, after that, we have this demonstration of nano-FTIR experiment using a thermal source, which is amazing because the thermal source, it's a powerful source, but there's no polarization there, and the source is also very big, so it's a geometrical source. So to focus this at the tip with good efficiency, it's a pain. I guess Florian really worked in this like crazy, and but the data is here, and this paper is particularly important for me because when this paper came out, all the synchrotron community was aware that, okay, if this is working with the thermal source, it's going to work very nicely with the synchrotron that's polarized, has a higher brightness and stuff. So I think I have a job because of this paper, maybe. I was hired in 2012 to construct the first beam line there. So it was right after this. And we bought the first instrument from NISPEC in 2012. It was like it was really important, that we found that there was something that would work for sure in the synchrotron. But the first demonstrations came from first PTB in Berlin. And then I know that in Japan they did some work, but ALS in California, they really did a good job, let's say, bringing the technique to the users community. And we came after that, right? Okay, and finally, I find this work also very disruptive because it's a sort of, I don't know, it's a brand for the nano-FTIR, I guess. So everybody that thinks about nano-FTIR, they visit this paper and they see like it's a simple demonstration, but now with a better source and a really good spectrum here. You can take from polymers, you can see, you can differentiate polymers. So I found this work also really important for the field. So after that, I think nano-FTIR became a standard thing in this GNOME community, I guess. You can correct me. But yeah, so I just want to highlight this. So in this talk, I will give a little introduction. It's not so little, actually, an introduction on Fourier transform spectroscopy. I think this is something that we use many parameters that in the nano-FTIR experiment that we don't know from where they come. So this is actually already practiced in the classical FTIR experiment. And so I will talk a little bit about this. I will talk about apodization and leakage, how you define the bandwidth of the experiment, resolution trade-off, so how actually can you choose whatever resolution without any loss? So that's a question. Some effects that we can handle with some post-processing. It's a 1.5 hour talk, so we can have a break, maybe. Let's see how the time goes, right? Questions or something. And then we make the bridge to the nano-FTIR. So we bring all these concepts of classical Fourier transform infrared spectroscopy to the, let's say, to the nanoscale. And I will revisit a little bit what the previous talks did. I think we drank lots of cider, so maybe we forgot some of the concepts. So I will just revisit. But now it's more comfortable because I had already the backup of Rainer and Martin and the really good talks before that they presented all these aspects. But then I will go through more practical aspects of nano-FTIR, like you know, understanding asymmetric interferometers and interferograms, how this is actually happening, why it's happening, and then I will finish, okay? All right, so the first thing is just a quick comparison between, let's say, dispersive spectrometers with the interferometers. So why using an interferometer, right? And there are a few advantages here that are important to point out. One is the multiplex advantage, which is called also the Felget advantage. And basically, it tells us that all resolution elements can be measured at once if you have an experiment like that. Something that's not possible with the grating experiment. And the other advantage is they call the throughput advantage, or the Jacquinot. advantage. And in this case, we're talking about the power that gets to the detector. So in the interferometer, you can get more radiation between the source and the detector for each resolution element. So that's basically the efficiency of gratings and stuff. All right, so we're going to be talking, of course, about interferometric things. All right. So I know that everybody knows this. I would just give some names here, and I think as we are recording this, this could be good for future students, I think, right? And yeah, that's the microsome interferometer. We know that we have the source. We have a beam splitter that divides the beam in two arms. One arm is fixed. We have a fixed mirror, and the other one you have a movable mirror that you can, let's say, change the phase relation between these two beams, right? They come back to the beam splitter, and then they go to a detector. Okay, so we have some names here. One very important is the optical path difference, OPD. It's related to the retardation of these waves here, or these fields. And the other one is the zero path difference, is when the two arms are equal. And it's not exactly the white light position, but let's start with this. It's related to the white light position. When you have the delays introduced by the sample, of course, this doesn't happen exactly when those two are equal, right? But I will talk a little bit more about this. So if we take an ideal example here, which is taking a monochromatic source and a perfect 50% beam splitter, and you add those fields at the detector, that's the kind of intensities that you have. So you are adding two sine waves there, and you have, for different positions of this movable mirror here, for different delta here, or OPD, you have different, let's say, interference conditions. You can have totally destructive, and you can have constructive again. And this is basically something that's proportional to the wavelength, right? So if we now look at the signal at the detector, that's the kind of signal that you have if you have this monochromatic wave there, right? So we have a DC component here and an oscillating component here. This one doesn't matter that much for the interferogram. In the end, the interferogram is really the part that oscillates. And that's the kind of signal that we have at the detector. But in a real case, you have more things here. You have, you know, this energy is never, let's say, ideally monochromatic. You have the detector sensitivity. You have also the environment that needs to be taken into account. Right, so in the end, you can call this whole function here as B. So in the end, you have an interferogram. That's this B multiplied by this cosine. This is basically a cosine Fourier transform of this B. So here there is already an indication that there is a relation that brings you from the interferogram to the spectrum and vice versa. All right, so this is basically a property of the Fourier transform, right? So the Fourier transform, if we think about events happening in time, the Fourier transform gives you another perspective, more like sort of weighted histogram of these waves in the frequency domain. So you can see here just an example of two waves, and you can see these two delta functions here. The amplitude is weighted by the amplitude that you see here in the waves before the transformation. And just to remember, if you have two frequencies, if you have a Fourier transform of this, you have this, let's say, sum of these two sine waves. If you change a little bit the amplitude of one of those, we still have the same structure. You change a little bit this valley here. If you have a more continuous spectrum, the transformation also show some oscillations in the interferogram, but now it's more, let's say, damped. So you have a quick decay here. And if you have a little bit broader, this guy here becomes a little bit narrower. So this is a relation really important that we're going to see all the time here, this Fourier transform property. So now, if we go to more realistic source, not, let's say, delta function source, we can have the example of thermal source, right? So the thermal source is basically a hot filament, right, in a certain temperature, and using the Planck's law, you can actually predict how's the emission in a certain energy range. So now that we have a very broadband spectrum, of course, we have a very narrow interferogram, as we showed before. And this is basically because of the Fourier transform of this broad thing here, this wide thing here, becomes a very narrow interferogram. In this case, it's a real example. So this is actually an interferogram taken in an open air environment. And you can see here that it has all these water vapor lines here that comes from the environment, CO2. But the nice thing is that let's say the shape of this curve here is very close to the emission, so to the predicted emission. So the detector was quite linear in that sense here to see this, but it has some features here. This should come from the detector. But yeah, so this is a more realistic situation, and yeah. So you know, the title of this talk is nano-FTIR, right? It has Fourier transform. So I will talk about this a few times more. And so if you have a single frequency, we saw that we can have the interferogram is actually the Fourier transform of this B function here. And that's what happened. So you come from the interferogram and go to the spectrum and vice versa if you actually do the inverse Fourier transform. But if you have like a more continuous source with more wavelengths there, it's better if you use an expression like this instead of just one term like this. So that's basically what I showed before. So here the only thing is that we can take the inverse Fourier transform, and we can have the more common situation is that you have a spectrum when you transform the interferogram. In this case, these are all real quantities, but we know that for the nano-FTIR, we must have complex Fourier transforms. This is very important because we want to use both amplitude and phase, or imaginary part and real part of the signal, so or the scattering. So this is important we need to use let's say the formal Fourier transform for that, right? It's just to remember. All right, so this is the analytical form, right, of the Fourier transform. So, but in fact, we have a discrete acquisition all the time. We have your acquisition board there that takes points with a certain sampling rate, and that's it. You have points, not like a curve. And here I found this pretty nice. It's a nice gift from the guys from the Solar Synchrotron, and this is an animation that they did showing how is inside an infrared spectrometer. So you can see there. We can see all the things that we saw before. So we have the source here, we have the beam splitter here, we have a fixed mirror here, and we have the moving mirror here. So that's, let's say, a kind of, this is a professional work of animation. That's why I found it so beautiful. But the point here is that you have this mirror traveling here, and you have some electronics to get these points, these data points, right? So we need to be, let's say, aware that we need to use discrete Fourier transform for that. And I'm almost done with the Fourier story, but this is basically the same as this, but now with discrete points, right? One thing that's important here is that it's discrete, but it's still a kind of expensive computation process. It's not so, we know that nowadays we have powerful computers like personal computers and stuff, but back in the days that they developed those interferometers, this was an important issue because in the end, this kind of transformation requires n-squared complex multiplications. So this is pretty heavy for the computers in that time. And yeah, so that was a sort of challenge. All right, so then it came the idea, that's not so new, of the fast Fourier transform. And this was actually an idea from Gauss, right? This is actually after he was dead. And, but he developed this many years before that. And the idea is to simplify this Fourier transform, the discrete Fourier transform, in a way that you can calculate this with just like summations, or let's say less complex multiplications. All right, so but this algorithm did not become very famous with this paper, but actually in '65, when Cooley and Tukey really presented the idea in a way that you can implement in machines, in the data acquisition. So this is, I think this is important to tell you because, you know, you go to whatever calculation software, you just have a library there that you have a FFT, right? And it's a black box. It's amazing, right? Gives you your spectrum. But this was actually a huge improvement in the, let's say, in the acquisition technology. We took this discrete Fourier transform that I showed you before, and what Tukey and Cooley did is just like put this in a binary base, and they could just write this exponents here in the binary base, and they could actually separate in two sums here. If you resolve one, and then you put the solution of this first sum into the outer one. So the flux of the, this is an example of a 4 points interferogram, which is just for example, right? But here you can see that you have the interferogram, you have the first sum here, and you see the path of this data. Somehow it goes dividing the data, and then you have the outer sum here, and you have some simplification here that can tell you that this is W0, this is minus W1, this is W1, this is minus W0. There are some cyclic simplification here. But the point is that you have here W0, W1, minus W0. So now you understand why all the time that you do this fast Fourier transform, you have this mirror image here. The algorithm divides the data points in two sets, and that's why you see that, right? And so in the end, the great advantage here is that you do less complex multiplications doing that. Instead of n squared, you do, in average, n complex multiplications. And you see here that n being like a base 2 number, it's easier to do all this. That's why all the time we define the n of our interferogram. We put, I don't know, 1024, 2048. It's like it's almost a base 2. It's always a base 2 number. It's just to make the FFT, let's say, easier to handle. All right, so now that you know how to do FFT, right? So let's see some, let's say, practical points of the data processing. So let's see, how long it was so far?
So far it was half an hour.
Okay. All right, so let's take an example of a spectrum of 2 lines again, so like a doublet, right? This is basically the sum of 2 waves, 2 sine waves here, and that's the interferogram that you get summing those waves, adding those waves. All right, so as you can see here, you have a sort of periodic structure here in this interference pattern that basically you have here, let's say, the out-of-phase valley, and then you have again a peak here that it's when you have most of the waves in phase, in this case 2 waves. Right, so it means that to solve these 2 peaks, you need at least one of these structures here. Right? So it means that we need at least the inverse of this frequency difference here. And this is basic what we do when we define the travel of our mirror as we want to resolve a certain frequency, right? So this is the minimum optical path difference required to solve this delta ni here. All right, so if you take a certain instrument and you have the maximum travel of your reference mirror, that defines your maximum resolution, spectral resolution. That's the relation between this, let's say, this mirror modulation and your spectral resolution. So, but there is an important problem here, is that your travel is always finite, right? So it means that you're always multiplying your ideally infinite interferogram by a truncation function. In this case, as the mirror just stops and go back, you have a boxcar function because you have data inside this range and no data outside this range. So that's the truncation function that you naturally multiply your interferogram when you measure a spectrum, right? And so basically your measurable spectrum is actually the Fourier transform of this convolution here, this multiplication here. That's your ideal interferogram multiplied by this truncation function here. That's what you measure. All right, so now in a more, let's say, pictorial view, so let's say that you have an infinite interferogram with these 2 frequencies, and if you Fourier transform this, you have these 2 delta functions, perfect, narrow, and that's it, right? But you cannot probe actually an infinite range in your interferometer. So you have a truncation function there. And if we take the Fourier transform of this truncation function, it's actually this well-known function here. As this is a boxcar function, this is a sinc function, right? And in the end, what you do is you multiply this function to your interferogram, and you Fourier transform this figure here. And that's what you get if you don't do any processing in your data when you collect your spectrum. So this is two examples, one for a larger truncation function. This is a narrow truncation function, so that's what you get. So we can call the convolution theorem here that tells us that the Fourier transform of a convolution of 2 functions is equal to the pointwise multiplication of the Fourier transform of each function. So in the end, the measurable spectrum is equal to the convolution between the real spectrum, and this function here, this f function here, that's basically the truncation function, or some people call this instrumental line shape function. All right, so we can see that this boxcar function doesn't seem to be ideal for, spectroscopy, for something that we want to really resolve peaks like this, right? Not a delta function, but peaks, right? So these oscillations, they are actually undesired, right? So it means that the sync function is not a very good, let's say, instrumental line shape function. For that, we must find smoother functions to actually deal with this fact that we have always a finite resolution, right? So we call this apodization. So apodization is basically, instead of using let's say, the natural truncation function, you define a function that you multiply your interferogram before transforming. So when you do that, you can have let's say, a more smooth decay here, and this actually becomes more, let's say, suitable to resolve infrared bands, right? Okay, so this problem is called leakage, and the solution is apodization. And there's a big list of apodization functions that you can find, and you can actually adapt this to your instrument. You can see what is best for you, right? Okay, so now talking about the bandwidth of the, let's say, the measurements, right? So what's the smaller number of points that you can have in an interferogram that could be proper for measuring? So let's remember the Nyquist criterion that says that an analog signal of with the frequency Ni can be, let's say, digitized with no loss of information if your sampling rate is 2 times this frequency, at least. So that's the Nyquist criterion. So now let's start to define an experiment that we have, let's say, the maximum frequency or maximum wave number that we want to measure. And with that, we have, of course, this Nyquist frequency here defined. Then we define also the resolution that we want to measure, these 2 parameters, right? So once we define those 2 parameters, we can actually calculate the number of points that we need to have there. And basically, we calculate that using this Nyquist criterion here. We just basically take the whole, let's say, frequency range after we apply the Nyquist criterion, and we divide by the spectral, let's say, spacing in the spectrum domain, right? And with this, we have the number of points, let's say, in agreement with the Nyquist criteria. We can also write this in function of the optical path difference and also the minimum step in the interferogram. But we have already our answer here. And I will show you an example on what happens when we don't follow this criteria. Let's say that we have an event that's happening in this frequency f here. And let's say that we are sampling this event here with a frequency 2f. So for this case here, I think the Nyquist criterion is fulfilled, right? So, and then we have this second, then we have this second example here, which is an event that's happening a little bit slower than the first one, in a smaller frequency, lower frequency, right? So in this case, sampling this event with the 2F sampling rate is still okay. But now I have here an event that's happening with a frequency that's higher than F. So it means that the 2F doesn't hold anymore, right? So in that case, we can visualize better what's the problem here. If I make these lines a little bit invisible, and here you can compare these two guys here, and you can see that they are the same. But this one is not good. It's not a real measurement. Has an artifact because we didn't follow the Nyquist criterion. So we call this aliasing, right? And this is really important to follow. Then it's not really a recipe to define n, but you can get really, let's say, wrong data if you don't follow that. All right, so yeah, just for you to remember those that already being done nano-FTIR. Let's take a case that we have, like, say, 2000 as the maximum frequency I want to measure, and the resolution is about 7.8 wave numbers. In this case, the minimum number that you must have there is 512 points. Okay, so now the resolution signal-to-noise trade-off. So here, I just bring the uncertain principle just for us to have an idea that if you have an event that you observe for a long time, you always have, let's say, a good precision in the frequency domain. But the other way around, if you just observe an event for a short period of time, you actually have a huge, let's say, undefinition in the frequency range. So that's basically the uncertain principle for the Fourier transform. We could see that already in the, the range that we scan the interferogram. You have more or less resolution in that, right? So I took here just a quick example that we have an interferogram with, we have two interferograms here. One is shorter than the other, but they overlap perfectly in this region here. So it means that I have different number of points, but I have the same density of points, right? So it means that I keep the bandwidth fixed back in the Nyquist criterion, right? So I keep this bandwidth fixed. So in this case, as I have different optical path difference here, I have different resolutions, right? I actually double the resolution when I double this path here. This is an important point. So this is the interferogram, and this is the Fourier transform of this interferogram. This is just a sinc function that brings you to a boxcar function or step function. All right, so, so here we can define, let's say, the ratio of this, let's say, improvement in resolution as I called here just Ni ratio, right? In this case, it's 2 because we are moving from 12.5 to 25 centimeters minus 1, right? So actually, I'm actually screwing up the resolution, right? Yeah, sorry about that. So in the end, to keep the same, maybe I did this wrong, huh? Oh, this one has less resolution than this one, right? Yeah, so it's inverted. I'm sorry about that. So, but in the end, the ratio here is 2. It means that you double the resolution from one condition to the other. And the result is that to keep the same total time for your experiment, you need to, as you double the points, you need to have half of the integration time for each point, right? So you're losing signal to noise in that sense if you keep the same conditions. So in the end, this loss scales with square root of this improvement of the resolution. So the signal to noise, then if you have a resolution that's, let's say, a little bit worse than this in a factor of 2, you're going to have 70% decrease in the sensitivity or the signal to noise ratio, right? So that's the message to take home. When you choose, let's say, better resolution, you lose sensitivity. That's the trade-off, right? Nothing is for free. All right, so the last thing that I want to talk in this first part is this effect, which is a funny effect and also sort of a magical solution for this effect, is that first of all, you have numerical computation and you always generate this uniform sampling values. That's something known, right? And sometimes the information between two data points in the spectrum domain is missing. And why they call this picket fence effect, right? So I have here an example. So you have your interferogram, again with this doublet example, right? And you have your spectrum, but actually you need to multiply this by an apodization function, and finally that's the real thing you get, right? And here you can see that we have some data points, but we have no idea if there is more than one frequency here. There's no valley here in the middle, right? So basically, they call this a fence effect because if you put this fence here, is your sampling rate, right, of the points, and you have something in between that you are not seeing, right? So actually, there is something you can do, which is just add some zeros here. It's like do something doing nothing, right? And you can increase virtually the number of points you have there. It doesn't mean that you are increasing the actual resolution, but this, let's say, these possible points that you can get in your spectrum, they get, let's say, a more precise information that, of course, the linear interpolation here is just too rough, right? So when you do that, you virtually increase this confidence of these points in the middle. That's what you do, but you still have the data points here, and you have now a shape that looks more like a doublet, right? So usually people practice a factor of 2 or 4. I don't think more than this can do much here, but that's maybe when you see a spectrum that sometimes has the double of the points that you set, maybe the software is adding some zeros there to deal with this effect. Okay, so how long we have?
55 minutes.
55. So what we've learned so far. So we went through the advantage between interferometers and grating spectrometers. FFT is a key algorithm for this business, right? And the maximum optical path difference defines your spectral resolution. Apodization minimizes the finite resolution effect. The number of points in your interferogram defines the bandwidth of your measurement, the Nyquist criterion. Zero padding help you to deal with the picket fence effect, and there is a trade-off between spectral resolution and signal-to-noise ratio, right? So I think, I don't know if it would be good. We can have maybe 5 to 10 minutes break just to go to the bathroom and come back, and or maybe some questions.
I think we take some questions, yeah, and then we maybe do some exercising, yeah.
I'm sorry, we didn't get to the near field still, right? But
Right.
now you know everything about Fourier transform, infrared, and we can go there and see how it works.
Maybe I should add here what Raul was really telling you is very important. You saw the guy with the camera coming to the front, right? And he has a very nice objective. So what he says, what Raul was telling you in the spectral range is exactly the same thing in the real space. Because if you take a diffraction limit, for instance, it's the same apodization because he has a very nice, expensive objective, and he can really do a lot by changing the appearance, what you see with your eyes, by doing exactly the same thing what Raul is saying. So this is very important that you grab this essence of spectral and spatial resolution limits and fencing stuff, right? So it's really universal, very important. Yeah.
Thank you. All right, so let's have a...
Okay.
Oh, yeah.
I'm sorry to put away attention from Fourier. It's very important, of course, but my question is about synchrotron, actually. The very, very first part. Like I noticed from the photo which you presented that your beam is, as far as I understand, it travels free space from like one piece of building, let's say, to your optical table and also further inside this tube. I mean, usually in optics, we try to keep this free space part to be as short as possible and preferably on the same optical table. I mean, do you have any issues with whatever vibrations or some instability? Or is it not free space there?
Okay, so first about the environment, right? So that's the accelerator. We have a big wall here. And then we have this vacuum path here. So this is all in vacuum. So the infrared is traveling here in a good environment, right? When we deliver it to the table, what we do is some purging. It's like purging boxes, and that's it. But it's free space, but it's in vacuum, right? But
I'm just wondering about the vibrations or like small change.
So,
I mean,
so
okay,
now,
it's mid-infrared, so it's not so crucial, but still.
It's a good question, actually. So we have here more or less 4 meters from the source to the window here. And the experiment goes a little bit more here, maybe 2 meters. 1 meter, 2 meters to get to the tip, right? So we have the optics that we extract here, and this optic is a few meters away. So it means that we need to design these optics in a sense that I need to define a criteria here at the tip. Criteria like I can move my beam no more than 5% of the full width at the maximum height. When I define this criteria, I put all these requirements in the optics, so the optics should be stable, and also the figures of merit of the optics should be also, let's say, consistent to this. So you're right, it's a fancy design. You need to take care of stability, the stiffness of all the elements that are holding there, the chambers, and so on. About the floor here, that's an important thing to say. So as this is a X-rays machine that works at the diffraction limit for X-rays, so it's a coherent machine for X-rays. So you need to have, we are talking about angstroms, wavelengths, right? So to have this X-rays beamlines, they had to design a floor here that's highly stable. Even if a truck is traveling outside the building and you have this, this sound wave that come, or even the vibration from the ground. So they designed this floor to actually kill many frequencies in those ranges. So infrared, we somehow take a ride in these fancy designs for X-rays, right? And it's cheaper. The beamline like this costs 1/10 or maybe 1/20 of an X-rays beamline. So it's still, I mean, you can see that's fancy, but inside the synchrotron world, it's okay. It's all fine to do this sort of things. I don't know if I answered you.
And, sir, what about the beam shape? Does it look nice, the beam shape, or is it like Gaussian-like, or is it like complete mess?
It's not Gaussian, but it's not messy as well. So it's here. I would say that we designed to produce here a secondary source. So we take the beam that's divergent from here, and we have an optics here that we focus after a few half a meter, more or less, and we produce a focal point that was designed to be in the near infrared range, that we have cameras for that to check. It was supposed to be around 15 microns, more or less, and round. And that was what we got. So somehow, at least for this machine, the old machine was messed up. So it was a real complicated beam. But this one somehow has a very well-behaved beam, so we could reproduce this focal point. And when we collimate this, because it goes divergent after that, and we collimate with a simple Thor Labs parabolic mirror, and the divergence is pretty good, I can say, because we propagate the beam in around, I don't know, 10 meters, and it doesn't grow more than 1 millimeter, which is in the visible range. So in the infrared should be even better. So yeah, so I think it's, I mean, I cannot say that's Gaussian, but it's becoming better, the optics and the beams in these new machines.
There's a quick question from Adrian.
I was visiting you, and I noticed that the air condition was playing also a role on the beam stability. So of course, when the beam is inside the shielding wall, inside the vacuum pipe, everything is good. But what we noticed is that if you have a long propagation of the beam on the optical table, when we switch on the air condition, we could notice that the visible part of the beam, the visible range, spectral range, it's a bit shaky because the refractive index of the air is changing, and then this could modify a little bit the beam path. But when we were cutting the visible part, the visible spectral range, and we look only at the infrared component, this was extremely, extremely stable. But what I want to say is that you have to pay attention if you have air condition inside your room, and especially blowing near your optical table, to check for the stability, not only of the AFM, but also the optical signal. When the beam is inside the housing of the microscope, then everything gets fine. But if you have a long propagation, this could slightly affect the stability of the visible beam.
It's a good point. We had 2 meters of in air by that doing that test, right? And it's a sort of mirage effect. So somehow, I think the beam is very low power. I don't know if you could answer me if, you know, it could be more sensitive to the environment. Of course, you have less, let's say, less power, and but yeah. So this is something that we saw. The beam shaking only with this convection of. Also, the humidity is high there. I don't know if you know. The air conditioning is more dry, and then you have this convection of different, very different humidity. Could be the effect.
Okay, I suggest we make a...
Kaiman has a question.
Fritz, okay.
Well, I would like to know what is the kind of power which arrives at the detector?
That's a good question. It's pretty low.
Is it several microwatts?
It's few microwatts.
Few.
Yeah, so...
so my question is really, I mean, we do have this other broadband system also in that range. And the question is, in the Fourier transform experiment, the only time during your sweep when you have high power really on the detector is in the white light position. Yeah. So, and there the problem could come if the detector is near its saturation point. We had that yesterday. Yeah. So it's less responsive at higher powers. That distorts that pulse, I would call it. And so you get a bad spectrum. And so how near are you to that with your microwatts? Did you ever try that out or find what the effect is?
I would say that right now we are pretty far away from the saturation, and as far as I understood is this, right? And we have this beamline here is still new, and it's in let's say in a transition phase. So we are taking just part of this beamline was designed to be actually a diagnostic beamline in the visible range. So the port that we have here is very small. So we're going to open that port a little bit more. But right now, the infrared that's reaching the tip, it's about 14 microwatt. So the fingerprint range, which is pretty low, right? And but it's very stable. That's the whole point here. So we're going to expand this to an inch instead of 5 millimeters of the port, and then the power is going to be around 350 microwatt in the infrared range. So this is the standard. So this is what we had in the older machine as well, but here we expect to have a better experiment just because the optics is better now. So, but that's the kind of, and we used to saturate the detector with the reference beam. We used to use a little bit of the iris to decrease that reference beam when we have this let's say this full condition.
I'd say we just making a 5-minute break now. Basically, stretch your legs, digest Nyquist noise and whatever, and we'll be back in 5 minutes from now, and then we have enough time to go on with questions.
Okay.
Thank you. Okay.
Yeah, I can talk to. Oh, sorry.